Just wait a minute. Yeah, I think it should be good now. Okay, so in the last class we were looking at duality. We were discussing a bit more about the duality and some of the interpretations. Okay, the geometric interpretations, and we also saw that the dual is always it's a convex optimization problem because the dual function is always a concave function. Okay, and the dual is always a lower bound in the form that we consider. It's a minimization problem. The original primal is a minimization problem, and the dual is a lower bound. Okay, and we talked of this duality gap, and then we were seeing this example, like one of the examples, we saw that the primal and dual values match, and so that's when we say strong duality holds. And then we were looking at this other example of, where the domain is in the space of integers. It's an integer program. Okay, and so this is not a convex optimization problem. And in this case, we were working this out and we were writing the dual where, when I wrote the dual, I mean, the dual function was exactly this min of these functions. But then when I drew it, there was some issues. So I just drew it more formally with a tool. Okay, so if you plot these 3 lines or 4 lines, what you're going to get is some plot like this. Okay, so you can just go back and check it if you haven't already done. So the dual function is, I mean, these are the various lines, and it's the min of all these lines. It's the piecewise minimum of all these lines. So in that sense, the dual is actually in this range, it's going to be this line. Then you're going to get this line, and then you're going to, in this range, it's going to be this line. So this is the dual function. You can see it's convex, but may not be smooth because there's some sharp edges here. Okay, so finally it turns out that the dual function boils down to this piecewise linear function. Okay, and if you maximize the dual, that's at this point. Okay, so that is at the point mu equals 2. And the value of the dual, the optimum value of the dual is -6. And the primal optimal we got was -3. So the dual, so there's some gap here. So P star and D star are not the same. There's a gap. So this is a case where strong duality doesn't hold. Okay, so I wanted to emphasize a couple of things here that, strong duality may not hold always. And the other thing is, this dual concept is something you can apply for not only continuous optimization problems, you can also apply it to, when your domain is a discrete set. Okay, so these are some of the things. So we saw some examples where strong duality holds and an example where strong duality doesn't hold. Okay, so in general, when does strong duality hold? Okay, so again, the problem that we are considering is something like this, where you want to minimize the function and you have some inequalities, equalities. Now, sufficient condition for strong duality is, one thing is when all these functions are convex. So f, g, and h, these are all convex functions. Okay, and in particular, h, j equals x, if the equality constraints, if those are convex, there is no other way but to have affine functions, affine or linear functions. Okay, so in particular, when you have f, g, and h satisfying these, so in some sense it's a convex optimization problem. When you have that, then there is this additional condition. So suppose there is an x naught, okay, which lies in the interior in terms of all these inequality constraints. Okay, and all the equalities, it's first of all a feasible point, and it lies in the interior as far as the inequality constraints are concerned. So Gix is strictly less than 0 for all these I, and the equality constraints are satisfied. So this is called a Slater point or Slater condition. So we saw this earlier in the context of the KKT conditions, right? And where we saw it, it was in particular about, instead of regularity conditions, when do you have that KKT conditions will be satisfied by an optimum. So in that case, we saw that, if you have this same condition, the Slaters condition, if it holds true for a convex optimization problem, then you're guaranteed that the optimal will satisfy the KKT conditions. Okay, so that's just to put in context where we saw the Slaters condition. Now here too, the Slaters condition, if it gets satisfied for a convex optimization problem, then it turns out that strong duality will hold. Okay, so and in particular, the lambda and mu that you solve from the dual, okay, that will also appear in a KKT point. Okay, so that's the result in this space, and maybe we'll just see an example. So the implication of this is that, if you solve the dual, like, finding a KKT point, there are a lot of steps that you go through, right? Like you try to find which are the, active constraints, and then you try to generate all possible active sets and all that. Okay, so now in this case, one implication is that when you have strong duality in a convex optimization problem, then what happens is that if you solve the dual, if you're able to find the lambda, the optimum lambda and mu from the dual, then directly you can use it in a KKT point. I mean, the KKT point will satisfy, these lambdas and mu's will show up in the KKT point. Okay, so let's just see one example of this. So I will just take one simple example. So this is the problem. So where you're trying to minimize norm of x squared by 2, subject to this linear constraint, A transpose X less than or equal to B. Okay, and in particular, B is given to be less than 0. So let's just see what this region means. So in terms of the feasible region here, what you are going to have is, so this is the, the axis, and A transpose X less than or equal to B is, A transpose X equal to B is some line like this. Okay, and less than or equal to B, you would look at this part. Okay, so yeah, so this is a line which makes a negative intercept here. So can you tell me why that's the case? So this is an intuition I'm giving in lower dimensions. It's a 2-dimensional space. X is in R2. So the line, this is the line A transpose X equal to B. Okay, now I drew it here and not somewhere in this part, right? So can somebody say why that's the case? Okay, am I audible?
Ma'am, both the intercept should be negative.
Exactly. So the intercept is negative, so that's why it comes on this part. And in particular, the origin is not included in this feasible region. Okay, because if you substitute the origin back here, what you're going to get is a value 0 in the left hand side, and the right hand side it's a negative value, so it doesn't belong to the feasible space. Now what you're doing here, in terms of the objective, you're trying to find a point in this half space. There's a half space. You're finding a point from this half space which is closest to origin. So which is the point which is closest to the origin? That's what you want to find from this optimization problem. Okay, so there are ways to do it. There are simple ways to do it. We'll also see how, it's solving this with optimization, what goes on here. Okay, so one thing is this is a convex optimization problem, right? So these constraints are, of course, they're linear, and so they're anyway convex. Okay, these inequality constraints, and the objective function norm x squared by 2, that's also convex, because you can just take the second derivative. It's going to take a value greater than 0.
So the norm, actually, it's the half the distance, right? It's not exactly the distance.
Yeah, exactly. It's half the distance, but in some sense, like, yeah, you in finding the one with the minimum of this half distance, you're effectively trying to minimize the overall distance because it's just the constant, and this half is there. It's just for some convenience, like when you take the derivative, so you'll get some 2 from the norm x. So you just don't want that interfering too much. You don't want to bother too much with constants. So that's why the half is there.
And you are saying that this is the distance closest to the origin because norm can be interpreted as a distance to the origin.
Yes, exactly. So this norm, you can think of this as x minus origin squared. So this is just this. So it's half of this distance. Okay. So
it is actually not just a line. It is the shortest distance to the entire half space.
Yes, exactly. It's shortest distance to the entire half space, this whole half space, yes. So if it was for the line, then you would have A transpose X equal to B. So that would be the shortest distance to this line. But in this case, it's the shortest distance to the half space, right? Yeah. So, okay. So now let's just see how we would solve this. So you can see directly that, there is a point in the interior. Okay, there's a half space. It's just a single half space, and of course there's a point which satisfies that A transpose X strictly less than B. So Slater's condition is going to be satisfied. Okay. Now, in general, when you have like multiple linear inequalities, provided this is a feasible set, you will have Slater's condition. It will get satisfied most often. Okay, so that is something that you can check. So Slater's condition is satisfied here, and so you have strong duality holds. Okay, without doubt. So let's just try.
So if we didn't have the less than or equal to, we just had equal to B, then Slater's condition is not satisfied, is it?
No, so Slater's condition, you have this, it's only for, the interior is only with respect to the inequalities. So for the equalities, they are satisfied, they have to be satisfied exactly. Yes.
Okay. So still the Slater's condition is satisfied.
Yes, even if you have this as equality, A transpose X equal to B, still Slater's condition will be satisfied. It's vacuously true. Provided this region is feasible, then it is going to be satisfied anyway. Okay. So, yeah. So, okay, so let's just try to write the Lagrangian now. So I will call this multiplier as lambda. So the Lagrangian function is going to be a function of X and lambda. So what's it going to be? Can somebody tell me?
Half of norm X squared, that is the function.
Yes.
Minus lambda A transpose X minus B.
So it's plus lambda.
Plus lambda. Plus
lambda A transpose X minus B. Okay. So if you write, in terms of the inequalities, if you write it, if the inequalities are written in this way, in the less than or equal to form, then you will have it as plus lambda. Okay. If it gets flipped, A transpose X greater than or equal to B, that's when you would write it as minus lambda. Okay. Okay. So this is the Lagrangian, and now suppose you were going to solve. Let's just see for a minute. Like if you had to solve the primal directly, so solving the primal also would imply like you want to find a KKT point. Okay. So solving the primal, one step would be you write the Lagrangian, and then you find the point X for which this gradient is 0. Okay, so that would, so this is actually X transpose X. So in terms of the gradient equal to 0, what would you get? Can you tell me the gradient of the Lagrangian?
X plus lambda A.
X plus lambda A. So X plus lambda A is going to give you 0. And so this would be X equals minus lambda times A. Okay, so this is one of the KKT conditions. And of course, you have things like it's feasible and you have complementary slackness. All those conditions have to be true. So the way we did was like you will consider cases, if, the optimum lies within the interior, then what happens? Lambda is 0. And if not, it lies on the boundary. And then what happens? So that was the approach we took to solve the KKT conditions. But now instead of doing that, let's go for the dual. Let's just try to see what the dual gives. Okay, so let this condition remain. We will use it later. So now I will just write the dual. So the dual function would just be that you want to minimize L of X lambda with respect to X. So here it's an unconstrained problem. X is an Rn. Okay, so you can just apply the, whatever you know of unconstrained optimization. And here the function is convex, L of X lambda. This is a convex function, right? Because half X squared, this is convex. And this is lambda is a constant, and then here also you have a convex function. It's affine. So overall, L of x lambda is convex in X. Okay, is convex in X. So you can again, use these conditions. The gradient of L of x lambda is 0, and such an X will be an optimizer for the Lagrangian as well. Okay, so this will again give me X has to be minus lambda A from above. Okay, so now let's just substitute what happens in theta of lambda. Let's try to simplify it. So substitute x equals minus lambda A here. So in half x transpose x plus lambda times A transpose x minus B. Okay, so you substitute this value of x. So this is going to give you what? So what's the first term going to be?
Lambda square A transpose A.
Yes, so lambda square by 2, A transpose A. Okay, and this term lambda A transpose X, what will it be? Can somebody tell me what this part is going to give you?
Minus lambda square A transpose A.
Minus lambda square A transpose A
Minus lambda B.
minus lambda B. Okay, so this is what you get as a dual function. This is actually minus lambda square by 2 A transpose A minus lambda B. Okay, and now in terms of the dual, you're interested in maximizing theta of lambda such that lambda is greater than or equal to 0. Okay, so again, what happens is, like you can first try to ignore this constraint, lambda greater than or equal to 0. And this function, theta of lambda, is a concave function. Okay, so this is something you can verify if you take, it's a concave with respect to lambda. So it's a concave in lambda. And so this you can see, if you take the derivative, the second derivative is just going to be minus half. So theta double prime of lambda is just going to be minus half A transpose A. And this is always going to be greater than 0. Why is that?
Norm of A.
It's a norm, right? So this is greater than or equal to 0, and negative. So minus half of that is a negative quantity. So this is concave. Okay, so again, you can try to set the gradient of theta lambda equal to 0. So find a lambda such that this gradient is 0. So what would you get then? What's the gradient of theta of lambda?
Minus lambda A transpose A minus B.
Yeah, minus lambda A transpose A minus B is 0. So now lambda is minus B by A transpose A. Okay, so this is the value of lambda. Now remember, this value of B is less than 0. The intercept is always negative. So because of that, this value is going to be greater than or equal to 0. Okay, so that's why this is going to be optimum for the dual. Okay, so so now we have found the optimum solution to the dual, and what we have is that Slaters condition is true. So strong duality is going to happen, and also we have that this lambda star is going to show up in the KKT point. So for the KKT point, we have that x is equal to minus lambda A. So now an optimum solution for the primal. So primal optimum you can get by just substituting this value of lambda. So is x star is minus lambda A. Okay, so this is going to give you lambda is B, so minus B by A transpose A. So this is going to give you B by A transpose A times A. Okay, so this is the value of x star. This is the optimum x star that you're going to get. Okay, and indeed you can also like try to verify from the KKT conditions by solving the other approach by taking what happens when some constraint, when this constraint is active and when it's inactive, and you will get back the same KKT point, this x star and this lambda. Okay, so so what this means is that the optimum x star is parallel to A. Okay, and it's because this B is negative, it's in a direction opposite to A. So the A would be something like this, right, in this direction, because if you look at the hyperplane passing through the origin, this would be A transpose X equal to 0. Okay, so everything that's orthogonal to A is on this hyperplane. So in terms of the optimum point X star, B by A transpose A times A, so it lies in the other direction. So something like this space. Okay, in this direction it lies, and you will see that it lies exactly on this hyperplane as well. So it will exactly satisfy A transpose X equal to B. So if you take A transpose X star, what you're going to get is B by A transpose A times A transpose A, and that's equal to B. It's exactly equal to B. Okay, so this will lie on this hyperplane. So this example, the purpose of this example was to give you some insights on how you could sometimes use the dual to get the primal solution as well, especially when strong duality holds. Okay, so yeah, are there any questions on this example?
Ma'am, I have a question.
Yes.
In Slaters condition, we had said that we wanted it interior. So g of x should be strictly less than 0. But here we're
Yes.
actually finding that the point is on the condition. So g is active. Then how are you saying that it's a Slaters point?
Yeah, so one thing is this Slaters condition, it doesn't mean that it's for the optimum point. So what Slaters condition is telling you is there is some point which lies in the interior. That may not be the optimum. Okay, so there is at least one point which lies in the interior, may or may not be optimum. So if that is true, it means Slaters condition is satisfied. Okay,
Ma'am,
so
but then in the previous statement, you had said that the same lambda star and mu star would be carried over.
So, okay, there are two things. So, Slaters condition is just telling you that existence of a point in the interior. Okay, so that is one thing. Now, if there is a point, such a point in the interior, now if you take the optimum x
Okay,
star,
yes, ma'am, it's clear. It's clear.
it could be a different point, right? So, yeah, so the lambda star, mu star, that would show up along with x star, which is different. It's not necessarily this point in the interior. Okay, so I think this might have come up for some of the others also. So remember that Slaters condition is always it is not telling you anything about the optimum point. So when you say that there is a point x naught in the interior, that is not necessarily the optimum. And all whatever other things we are telling about the KKT point, that is for the optimum, and that need not be a Slater point. Okay, so yeah, thanks Devyani for asking. Siddharth?
Ma'am, I didn't understand this discussion. Can we once have a short review of this latest condition?
Sure. So, yeah, so what I told you earlier was, if you have this condition, Slaters condition, then you have strong duality. Okay, so the Slaters condition is what it's telling you is there is some point. Okay, so there is some x naught, so something in the interior of this. Okay, so x naught is something here, so that these inequalities are satisfied strictly. So GIX is strictly GI of x naught. So maybe I should just make it G of x naught. Maybe that's what is causing some confusion. So there is a point such that for this x naught, all these inequalities are strict and the equalities are satisfied. So this is a feasible point x naught, because all these being satisfied means, of course, it's feasible for the problem. And in particular, these inequalities, all the inequalities are satisfied strictly. Okay, GI of x naught is less than 0 for every inequality you take. So that is what the Slaters point is telling you. It's just saying that there's a point in the interior. Okay. Now, what we said about if this condition holds, if Slaters condition holds, now let's look at the optimum x star. Okay, so this is x star such that it is f of x star is equal to the optimum. So this is equal to p star, and for this x star you have that f of x star is equal to p star. Okay, so this is different from x naught. This is not the Slater point. Okay, this is some point which is the optimum. So what it's telling is if you have such an interior point, if you have a Slater point, then the optimum that you take, that will appear as a KKT point. Okay, and that we know from the necessary conditions, right? I mean, if you have Slater's condition is true, then the optimum, if x star is optimum, then it satisfies the KKT conditions. Okay, now what this is additionally telling you is that strong duality holds. So under Slater's condition, strong duality holds, and x star will appear as a KKT point, the optimum. And in particular, the lambda and mu that you get as the dual solutions, okay, those will show up as the in the KKT point. Okay, so yeah, so that's what we just saw here. So here, the optimum x was something which lies on this hyperplane. It is getting satisfied with equality. But the optimum x is not the Slater point. The Slater point is something inside such that A transpose x naught is strictly less than B. Okay, something in the far interior that is such a point exists. Okay, so then strong duality will hold, and you have a KKT point. The optimum is this point. X star is B A by A transpose A. Okay, and the KKT point is this pair x star lambda star. This is going to be a KKT point. Okay, so just to verify this, I mean, you should just go and try to solve the primal on your own, like using the method we did earlier by choosing which of these is active, which is inactive, and then you will get this same x star and lambda star as a KKT point. Okay, so this is the two ways to get KKT points when strong duality holds. Okay, Siddharth, did I answer your question? Is it clear?
Yes,
It's clear. Okay, good. So yeah, so this is one use case. So it's kind of similar to in the case of LP dual. There also you had a convex optimization problem, and even there, provided your your linear program is feasible, then you're going to have something in the interior for sure. I mean, whenever you have these inequality constraints, inequalities as linear inequalities, and provided the region is feasible, this is always going to be satisfied. And there also we did some examples of how you could use the dual to get an optimum solution for the primal. So the same thing happens in general for convex optimization under Slaters condition. Okay, so now in terms of the uses of the dual, I mean, this kind of covers up the points I wanted to tell about the dual. Now, there's this application that I wanted to talk of in SVM, but I think you'll be doing that in the machine learning class. So I think this, I will not repeat it. So that's a classic example of where duality plays a huge role. Okay. Now, just to give you some more insight about where dual can be used, there's this area called robust optimization. So this is something which I've been working on for the past few years. So here, the dual is plays a really important role. In fact, it's many of the things that we do involve first writing the dual and then doing some operations. So I'll just give you a bit of a brief flavor of it. I'm not going to ask you anything about this for the exam, but this is just for, if you're curious about where all the dual can be used. Okay, so, like in all the optimization problems we have seen, we have something like, some function. Okay, so maybe you have, let me just say like, okay, I'll just take an example maybe. So think of this case where, you, just a second. Okay, so think of this example where, there's a guy who's running some business. Okay, he has a shop. Maybe he's selling some newspapers every day. So it's called the news vendor problem. So he's going to sell newspapers every day. And there's some demand every day that comes. So there's a demand P for newspapers. It could be any product. Okay, so let's just say it's newspapers. And there's this demand for this is daily demand, and he has to beforehand order some quantity. So So this is the quantity of items that he has to order beforehand. And he has to order this quantity based on the demand. Okay, because he wants to sell all. If he's getting some quantity of newspapers, he wants to order in such a way that all of them are sold out. Okay, because anything extra he keeps, it's useless for the next day. Okay, so newspaper is not going to be useful for the next day. So he wants to order the quantity so that the demand is met, and there's some profit, of course.
So this is like your vaccine also, right? If you take vaccine, you buy vaccine and you don't
Yes.
use it, it will get spoiled.
Yes, exactly. Yeah. So vaccine, there's something like you can keep it for some time, but yeah, maybe you can say the duration of how long you can keep, you extend it. You extend the length of a day, maybe. So that would be the vaccine example. Right. So it is relevant in any of these kind of situations where there is some demand, and if you cannot store things for some time, okay, because it gets wasted and then you have to dispose, and there's a cost also for this. Okay, so suppose there is for any of this there's some profit, right? So there's a profit which is a function of the quantity he orders, the shop guy orders, and it's also a function of the demand. Okay, it will depend on both these factors, and what the shop guy or the manufacturers, if it's in large businesses, it would be to find the quantity so that this profit is maximized. Okay, so this is the quantity he has to order that is within his control, and this is what he will try to solve. Okay, so this is the case. This is like a standard optimization problem. You could use some of the techniques we have learned to solve this. Now the issue is that this demand, it's not always known beforehand. Okay, there'll be some rough idea that you may have about the demand, but the exact value is not known. And many times these kind of optimization problems are very sensitive to these parameters. Okay, so you can think of this D as a parameter to the optimization problem. For example, in this case, maybe these A and B, these are all the parameters, right? So it's something like that. So these Ds are the parameters. And so in all the problems we saw so far, the D was fixed. I mean, the parameters we used, those were fixed. But in this kind of application, this demand also can vary. I mean, you don't know for sure beforehand. So at the time this guy is making an order, I mean, at the time that he orders this Q quantity, he's not going to know what is the demand, what the actual demand is actually. Okay, so that will get known only on that day, like once people start coming and buying the newspapers or the product. Okay, so this is a sensitive problem to the demand, and so what you want to do is, even if the demand is such that if the demand is very bad, even then you want to have some good profit. Okay, so typically what happens is D is uncertain. Okay, there's some uncertainty here, and say you have some idea about the uncertainty, so D lies in some set U. Okay, so it's not a single value anymore, it lies in some set. Now what is the one that what is the D which minimizes this profit? Okay, and there's some D which it is going to hurt you. If the demand is going to be very bad, it's going to hurt you. Now how can you order the quantity such that even if the demand is bad, your profit is reasonable? I mean, you do the best possible even in the worst demand. Okay, so this kind of a problem shows up in robust. So this is called a robust optimization problem. It's called RO. Now there are different ways. I mean, this uncertainty can come in different ways. So it could sometimes just be, an interval, and sometimes it could be like a polyhedron, or sometimes you know some distribution for D, and maybe you don't know the exact distribution, but you have a set of possible distributions. So there are different variants of this, but broadly this is the framework. Okay, so now this is like a two-stage problem. Okay, so how do you even go about solving this? Okay, so that is the whole question in RO. Now, the dual really helps in these kind of problems. So what you can do is, for this inner problem, so this is the two stages. This is the first stage, and you can think of this as second stage problem. And for this problem, if you take the dual, what you're going to get is something of this form, right? So the dual will be some theta of lambda mu, and it will also depend on q here because that is coming in the function. So it will come in this manner, and you want to maximize lambdas, which are great, over lambdas and mu's. So this is an optimization problem over lambdas and mu's. Okay, and then you have an outer max over q. Okay, so here what was initially a max min problem, because of the dual, you're able to write it as a max problem. So this you can just write it as a single maximization problem now over lambda, mu, and q's. Okay, so you can then just solve this problem. Okay, so that is another use of the dual. So yeah, I just thought this would give you, some better idea about where the dual can be used. So it gets used extensively in this robust optimization literature. Okay, yeah. So I'm not going to quiz you on this for the exams. So this is just to give further insights. Okay, so are there any questions so far?
No, no.
Ma'am,
Yes,
ma'am,
Siddharth.
in the last step, we actually took the Q in the inside. So does like in some cases, won't the order of maximization then matter?
Yeah, so here, if you have a single maximization, then it's not going to, if it's just a max kind of a problem, then it's not going to really matter. The issue is when you have this kind of a max min, and whether you do a min max, then things will change. Okay, so here you can safely do a joint optimization over all of them. Of course, this problem, it depends. It depends on the coupling between the lambda q, how it appears in the function. So whether it's an easy problem or not, that is going to depend on this profit function, this uncertainty set, and couple of these kind of issues. But in general, yeah, you can, when you have something like a max, it's not going to harm you to do a joint optimization.
Yes, ma'am. And ma'am, why do we call it robust?
Yeah, good question. So this, you remember, when we started off this problem, you assume that the demand is known, and that's the base problem is something like this. Okay, so when there's no uncertainty, this is the problem you want to solve. Now, what you're trying to do is, when you cast it in this manner, you're trying to make this optimization problem robust to these kind of uncertainties. Okay, so even if there is some uncertainty, even if the demand becomes very bad, what is the safe strategy? Okay, so that's why this is called robust. So it's like making the optimization problems robust to uncertainty. So that's why it's called robust optimization. Okay. Okay, so that.
Yes, ma'am.
Okay, good. Yeah, so one thing is also this robust optimization. Nowadays it's also coming in learning problems, because even in your learning, you have some kind of an optimization problem that you solve, and it's parameterized by data, right? So instead of D, you have some problem data, some samples, right? And many times, there is noise in the samples, and that's uncertain, and there are outliers and all those things that can happen. So even for those kind of situations, robust optimization nowadays, it's getting used in such situations. So there are many such cases. It's a more general framework where there's uncertainty. Okay, so so I think I've covered what I wanted to tell you about the dual. Now, so there were two things that I wanted to teach you as use cases after constrained optimization. So one was SVM and one was PCA. So SVM, you're going to do it in machine learning class, and we are also running out of time. So what I will do is we will just take up PCA as a case study. Okay, so let me just open a new window. Okay. Yeah, so what I will do is, I will just talk of some intuitions about the PCA and PCA method, and a view of it from optimization. Okay, so just before I go ahead, I just want to get a sense of how many of you are doing the high dimensional data science course. Are there people who are not doing that course? If you're not doing that course, can you just type in the chat box? Or if you're doing it, say yes. If you're not doing it, say no. You're not doing that course. Tushar, no. No. Okay. Okay. Okay, good. So I see a couple of you who are not doing that course. So maybe I'll just give you some insights about what PCA is doing first before getting into the method. So the idea is, in many of these learning problems, there is a lot of data. Okay, there are many samples, and yeah, maybe many samples of few samples, but the thing is you'll have a lot of features. Okay, so the dimension of the problem is usually large, so a lot of features will be there. So for example, something like, you can think of an example where you're trying to predict the price of a house. Okay, the real estate market, and you're trying to predict the price of a house, and you will have a lot of features there, things like area of the house, maybe you have area of the plot. Okay, and maybe you have something else like size of the rooms or things like that. Okay, so you can see that many of these features are in some sense correlated. Okay, so the area of a plot and area of a house, for instance, those are like very related features, and there's some there's some dependence between the two. Okay, so not all these features are very crucial in in your data, in any task that you want to do. Okay, so sometimes it even harms if you have a lot of these kind of features, then you're not able to figure out some pattern, because it is just unnecessary information. And the goal of PCA is to get some kind of a simpler representation of these data points. Okay, so just to illustrate it, so maybe like in even 2 dimensions, suppose your points are something like, if it's a classification task, maybe you have something like this. Okay, the negative examples are like this, and the positive examples are something of this form. Okay, so now if you just look at it, I mean, now we know that there is some line along this. Okay, so so there is some, all the data points are spread along this line. Okay, and if you get some kind of a projection along this line, so by projection you mean that instead of taking this point like this, you ensure that what is the nearest point on this line. I mean, what is the nearest value on this line to each of these points. So you will get some points in this manner, and similarly for these positive points you get something of this kind. Okay, so they'll be spread out along this line, and you can use just the values of these projections on this line to do a classification. Okay, so but instead, like if you project on some other line like this, then you will get something of this kind. So all these points will, they'll be all together, so you will not be able to get a good representation. Okay, and when the same thing happens in, say, some 100 dimensions, if you have some 100 features, then you're most likely not going to be able to figure out anything from just looking at the points. But
So
if you
so second line that you drew, the projection will be all mixed up, right? The pluses and the minuses will
Yes.
come together.
Yes, it will all come together.
Because
So
you're like they will straight line perpendicular to that will all come together. So it will be
yes.
like a cloud of points on the line.
Yeah, so there's nothing you will be able to figure out from this line. So, but if you project it onto this this vertical line here, then you get some more information. Okay, things become a little more clearer. Okay, so that's the kind of objective in PCA. You're trying to project it onto, trying to project the points onto a smaller dimensional space. Okay, so that you can see things a little more clearly. Okay,
So in this example, how did it become smaller dimension?
so these points were in 2 dimension. Okay, so now when we say that we project it along a line, Okay, so a line, you can represent it with just one vector. Okay, so a line is everything which is passing through, which is parallel to this vector, right? So it's about finding this vector, so that if you project onto this line passing through this vector, it's just you're just going to get one single point. Instead of R2, you're going to get a representation in R1. Okay, so that's the idea behind PCA. So that's how it simplifies. So instead of getting a representation, so something which was, say, maybe some R100, instead of R100, you're going to bring it down to something like maybe R2 or R3 or something like that. Generally, some RK. Okay, so sorry. So generally, some RK, you're bringing it down to a representation in the space of RK, so that things get a little more clearer. Okay. So yeah. Okay, so that's the underlying principle in PCA. So so what we have in with us, the tool that we have is this notion of subspaces. Okay, so the subspaces and affine spaces. So in particular, what PCA does is it makes use of a projection into a lower dimensional subspace or even an affine space. Okay, so so this example I drew here, this was a subspace. So if I say this is the origin, okay, suppose this is the origin, then okay, so this is the origin. If I say, so what I'm drawing here in this line, this is actually a subspace. Okay, so it passes through the origin, and it's a one-dimensional subspace, to be more specific, because to describe this subspace, what you need is just this one vector, and that is going to give you the basis for this subspace. Okay, and the objective is to find the some representation of this subspace. So what we have in terms of subspaces is the basis. So you want to find an orthonormal basis. Okay, for a lower dimensional, for a subspace of dimension k. For a subspace of dimension k. Okay, so that something like you don't lose a lot of information. The error is minimized. Okay.
So why should the projection lie in a subspace? I mean, it could be displaced also, right?
Yeah. So you could also have a case where this is the axis and your points are all something like this. Okay, so if you try to find a subspace, what you're going to get is some line like this, which passes through the origin, but that is not the best. So instead, it would be better to move it here to get a line like this. So this is an affine space. Okay, right? So ideally, what you want is an affine space. But now what you can do is, instead of, like this is a case where the representation of the points is given in some way in terms of these axes. So this is x1 and this is x2. It's given with respect to x1 and x2. Now, instead of, having this as the axis, you could rotate the axis in some way so that so the mean of these points is somewhere here. So maybe it goes to here. The origin can be moved to this point. Okay, so now you have a new, these points are still the same, but in terms of this origin, it's going to get changed slightly. So here, with respect to this space, if you can get another, the translation of these points with respect to this new axis, then you can find a subspace for this origin. So in some sense, these are equivalent. Okay, so instead of, you ideally want an affine subspace, affine space, but instead of that, you could focus on the problem of finding a subspace, and you can translate these data points into this region and then find a subspace. So the underlying main problem is to find a lower dimensional subspace for the points. Okay, so I think I don't have much of time to go through it right now. So we'll clarify some of these things tomorrow, and then I will get into the method as well. Okay, so I think I will maybe stop here for now, and I will hang back if there are any questions. If not, we meet tomorrow at 2 p.m. Okay, so thanks.
Thank you.